The last video went through a couple of examples of one-dimensional problems with constant velocity. This is going to be a different kind of one-dimensional problem with constant velocity. These are pursuit problems. I wanted to put these as a separate video because they do feel different. But it shouldn't be too bad. These are a special case of kinematics problems, and the idea is that we have two separate entities and we're trying to find where they meet up. So this is like that classic question of train A leaves New York and it's moving west at 60 miles per hour. Train B at the same time leaves Philadelphia moving east at 45 miles an hour. Where do they meet? We're going to approach these a lot like we did the regular problems, but for right now, let's not worry about trains. I'm going to give you one to start with. Alex starts at home and walks at 3 meters per second to the east. Bailey is going to start at her house, which is a kilometer east of Alex's house, and walks at 2 meters per second to the west. Where do they meet up? So I'll write this down for you first. And then we'll have to add. They left home at the same time. That's important. Here we go. Before, I set up this table with x initial, x final, v, and t, and I'm going to do the same thing again. X initial, x final, v, t. But now I want to do this separately for Alex and for Bailey. Names chosen just so they could start with A and B. Let's see what information we can get. We are looking for where do they meet up. So we want x final. We have Alex starts at home. So for Alex starts at home, x initial is 0 because we can pick that to be anywhere. Walks at 3 meters per second eastward. We've got separate information for Bailey. But to get this, I'm going to really draw a picture. Here is Alex's place. Here is Bailey's place. Bailey lives 1 kilometer west or east of Alex. I'm going to need a coordinate system, and my coordinate system, I've got everything moving on the x-axis. So that may as well be my x-axis. I can pick anywhere I want to be x equals 0, and I said that I wanted Alex to start at home and that was going to be x equals 0. This is x equals 0. But that means that Bailey's place, which is a kilometer away, this is x equals 1,000 meters. Alex starts off walking 3.5 meters eastward. To the right was the positive x direction. So Alex starts at 0, is walking at 3 meters per second, and it's to the right eastward, which we are calling positive. So now Bailey, I'll do Bailey's in a different color. Bailey lives 1 kilometer directly west of Alex and starts at her place. So she is going to start at her house, which is at x equals 1,000 meters. She walks 2 meters per second westward. So she's walking this way. That is 2 meters per second, but she's walking westward, so we get a minus sign on there. Where do they meet up? So we are looking for x final. We don't know what that is. But if they meet up, they are going to be in the same place at the same time. We don't know the time either. If they meet up, they'll be at the same place at the same time. So we can say these two are going to be the same as each other. these two are going to be the same as each other. And now I can get started. For Alex, x final, so for Alex, x final is x initial plus vt. We don't know x final, but it's the one we want to know, and we don't know t. It's still an unknown. I'm going to actually put it in a different color. I'm going to put it in orange. It'll look a lot like red, but not be quite the same. It is an unknown, but it's not the final unknown that I'm looking for. But I do know that my initial position is 0. Didn't get to do a whole lot with that, but so it goes. I've got two unknowns in this equation. I can't just solve it. So I'm going to look at Bailey's position. Bailey's position is going to work the same way. X final equals x initial for Bailey, which is not 0, plus vt. I have two equations with two unknowns, and I can solve this a number of different ways. I'm going to make sure to label this one v Bailey, v Alex. If they're in the same place at the same time, this x final is equal to that x final, I'm going to set this whole equation equal to this whole equation. Here we go. So this first one, x final, is v Alex times t, and that's going to be equal to this one, x initial Bailey plus v Bailey times t. I'm trying to get t by itself, so I'm going to subtract v Bailey times t from the right side and from the left. This leaves on the left v Alex t minus v Bailey t, and on the right it leaves x initial for Bailey. I have t in this term and t in this term. I'm going to factor a t out of these. When I do that, I will be left with VA minus VB times t equals x initial Bailey. If that factoring step is one that you saw and you thought to yourself, uh-oh, I'm not sure I would have thought to do that, this is something you're going to do a lot of, so it is worth getting comfortable with now. I'm trying to get t by itself, so I'm going to divide by VA minus VB over here and over here, and I am left with t by itself. X initial Bailey over v Alex minus v Bailey, and I can start plugging numbers in. X initial Bailey is 1,000 meters. V Alex, that is right here, 3 meters per second, minus v Bailey is negative 2 meters per second. And I get that they meet up. 3 minus negative 2 is 5. 1,000 over 5 is 200. They meet up after 200 seconds. Keep going, because I wasn't asked when do they meet up, I was asked where do they meet up. Now that I've got that 200 seconds, I'm going to fill in my table. I can plug that into either of these equations. The top equation is just a little bit simpler, so I'm going to do that. I'm going to take my 200 seconds and plug it in for t up here. When I do that, I get v Alex, which is 3 meters per second, times 200 seconds equals 600 meters east of Alex's place. That's a pursuit problem. I want to give you one more. I'll write it out first. Sammy starts walking to the park at a speed of 3 meters per second. 2 minutes after Sammy leaves, Sammy's little brother realizes he wants to go along. So he hops on his bike and he pedals hard and he rides at 8 meters per second. How long until he catches up? I'm going to start with a picture. There's a house. Here is Sammy walking along. And then Sammy's little brother is going to hop on a bike and pedal hard. Sammy's going 3 meters per second. Sammy's brother is going to go 8 meters per second. We want to know when or how long until they catch up. I will call home the origin. This is my x equals 0. And I'm going to say that to the right will be my positive x-axis. So then I want to set up x initial, x final, v, and t. For Sammy, I'm going to right away pick out Sammy is moving at 3 meters per second. I'm not going to really know when they catch up or where they catch up. Those are unknowns. But I do want to know when they're going to. I'm leaving x initial blank for just a moment. Sammy's brother, who I failed to give a name, so B for brother, is going to move at 8 meters per second. And Sammy's brother is going to catch up, so we don't know where or when. But the brother starts for sure at home. Now, at the time that the brother leaves home, we want to find out where is Sammy, because that's going to be Sammy's starting position. So I'll do that. Sammy's starting position. Sammy was at home, has been walking at 3 meters per second, so it's like I kind of have to do a separate problem, right? X initial, X final, V initial, well, just V and T. This is just for Sammy. Sammy initially started at home. We don't know how far, but we do know 3 meters per second is the speed, and it's been 2 minutes. 2 minutes, we don't like minutes there and seconds here, so we're going to have to say 2 minutes is 120 seconds. And we're going to do this problem. X final is what we're solving for, which is good because it's the only unknown. X final is X initial plus V T. X initial is 0. 3 meters per second times 120 seconds. Sammy is 360 meters into this trip. That value will be where Sammy is when the brother first starts moving. So that's my 360 meters. Now I can set up. For Sammy, X final which I don't know. I'll leave it for a second. X final is x initial plus vt. I don't know the time, but that's the one I'm looking for. I don't know x final, but x final is in the end not the last variable that I want, so slightly different color. For the brother, I'm going to have the same equation. X final equals x initial plus v t. I also know that for the brother, my x initial is 0. So I have two equations with two unknowns, because I know that if they are going to meet up, they have to be in the same place at the same time. So those have to be the same as each other. Those have to be the same as each other. Last time when I did a problem up there somewhere, I had x final be the final thing that I was trying to solve for. This time I'm trying to solve for t, so it's a little bit different, but only a little bit. I have these two equations with two unknowns. I'm going to set this side equal to this side. So x initial for the brother plus v brother times time equals v for Sammy here we go. X initial for Sammy plus v Sammy times time equals v brother times time. I'm solving for time, so I'm going to grab all the time things and put them together on one side of my equation. The left side is just x initial for Sammy. The right side becomes v brother times time minus v Sammy times time. I warned you in the last one, and here we are again. There is time, and we are going to do a little bit of factoring. V brother minus v Sammy times time is what we end up with on the right, and on the left we're still at x initial for Sammy. I'm going to divide by v brother minus v Sammy on the right and on the left, and I will be left with time by itself equals x initial for Sammy divided by v brother minus v Sammy. I can plug in some numbers. Here's my table up here. X initial for Sammy, that's 360 meters. V for the brother, that is 8 meters per second. V for Sammy is 3 meters per second. 360 divided by 5 is 72 seconds. That's how long it's going to take until they catch up. I didn't find x final, and I wasn't asked to, so I'm not going to. Right? That's the end of the problem. Sometimes you don't have to find every variable. But these are two examples of pursuit problems. They work just like the 1D motion problems. We're just doing the problem twice.